Hi, my name is Brian Bowman, and my demonstration today is going to be on generating a spark using an inductor. And the principle of operation here is that an inductor does not tolerate an instantaneous change in current through it. And it's governed by the equation V is equal to L di dt, where V is the voltage, L is the inductance of the coil, and I is, of course, the current. So suppose we were to send a steady flow of current through this inductor and then suddenly break the circuit, open the switch. This instantaneous change in current would cause a large surge in the voltage across that inductor, and we can use that to generate a spark. Now, as I've drawn it here, my diagram shows the spark occurring over to the right across a couple of electrodes. In reality, this circuit probably wouldn't function that way. And in reality, the sparking would occur across the switch as the switch is being opened. So this is a little bit of a problem that we have to overcome. This is a classic ignition circuit, and it solves the problem by breaking up the single inductor into a transformer, and also adds a capacitor around the switch to reduce arcing across the switch. So the transformer basically forces the voltage, the sparking to occur across the electrodes where we desire it to. This is actually this diagram, the circuit that I built my demonstration to originally. Unfortunately, I was unable to get any sparking whatsoever, so a little bit discouraging. But I did notice that with my voltmeter, I was able to detect some voltage fluctuations across the secondary inductor of this transformer. And so I thought I might try to put that to use, and so I added a couple of components, a rectifier diode and a large electrolytic capacitor. And the idea is, with repeated opening and closing of the switch, I could store up enough voltage, enough sustained voltage, to get a spark. And notice also that I replaced my simple mechanical switch with a solenoid actuated relay, basically a homemade buzzer, to give me that rapid opening and closing of the switch. Let me go ahead and show you my physical arrangement. See if I can capture all this here. And what you see here is the primary winding of the transformer. The secondary winding of the transformer is concentric to it. It's a much finer, much more tightly wound wire, and that's underneath the larger copper wire that you see here. You'll see to the left, to your left, the homemade buzzer mechanism. And one curious thing about the way I set this up is the primary winding of the transformer actually doubles as the solenoid actuator for the buzzer. So it's kind of a dual function there. It eliminates a component by arranging it that way. Over to the right, you'll see a large capacitor, 4700 microfarad, maximum 35 volts. And here is I don't know if you can see, it's a little bit smaller, the rectifier diode. And you'll notice that the voltage currently across the capacitor is basically negligible. But if we run this thing, you'll see that the voltage spikes up rapidly, and every time I run it I have to let it equilibrate for a second. Again, the capacitor is rated for 35 volts, so we don't want to go above that, but we want to get as close to it as we can. And that's pretty close. All right, so now we're ready to to use our capacitor to generate a spark. And I don't actually have to bring these in contact, they just have to be close. And there's your spark. So I hope you enjoyed my presentation. Thanks.